Welcome everyone in another session of TIFR Math problem solving. So today's problem is practically using the continuity. I mean the extension of the extension criteria for uniform continuous functions. So if you know what extension criteria for uniform continuous functions are, then it is pretty straightforward. If you do not know, you can actually look these theorems up in Bartlett-Sharbert or any standard real analysis book. So as you can see, the question is pretty straightforward. A function is given, and you are asked to find out that will they be bounded, uniformly continuous, not bounded but uniformly continuous, stuff like that. So the first thing is that if a function on sine of x cubed by x like this, if it is defined like this, and it is defined from 0 comma infinity to r. So the first thing that you need to visualize here is that even before going into the problem, even if before going into the solution, the one thing that you need to visualize here is that where should the boundedness be a problem? Because sine is anywhere bounded, right? So the boundedness problem comes when you get pretty close to 0. So that's, I mean, like, I'm not saying that it comes, the boundedness problems readily comes at 0. That's not what I'm saying. What I'm saying is that if it at all has a boundedness problem, then it would have been in a neighborhood of 0, because sine x cube is always bounded, right? So the only problem that it can make is the 1 by x portion. So we will see what happens at limit x tends to 0. So if limit x tends to 0 exists, then it is of course bounded. So if I take limit x tends to 0, sine x cubed by x, then this is, you can actually write that limit x tends to 0, sine x cubed by x cubed into x square. So this is 0, because like x tends to 0, you will have x cubed tends to 0, sine x cubed by x cubed, this becomes 1, and since there is x square, so you just put it, it will be 0. So the first thing that we see that the function f of x equals to sine x cubed by x is bounded. So how did we prove it? We proved it like this, that anyway sine x cubed by x is always in between 1 by x and minus 1 by x. So there is no problem if x tends to infinity, because then both of these will go to 0 if x tends to infinity. And then sine x cubed by x will go to 0, right? So the problem was when 1 by x, so when x is approaching 0. So that is one of those conditions when sine x cubed by x would have shot towards infinity. But since the limit exists, it cannot shoot towards infinity, the sine x cubed by x function. Okay, so this is the way that we are proving that it is bounded. So the boundedness is there. So now to prove the uniform continuity, this is something, for this you need to know the extension theorem. So I will write the extension theorem, extension theorem 1 and 2. So first of all, if from a comma b, where a b is in R, b to R is uniformly continuous, if and only if there exists an f tilde from closed interval a comma b to R, which is continuous, and f tilde restricted to open interval a comma b is nothing but f. That is why it is called as an extension theorem. So this is an if and only criterion for the uniform continuity. So if you are trying to prove a function is uniform continuous on a finite open interval, then prove that it is a restriction of a continuous function of a closed interval. Okay, so if you can prove it, then you are done. So this is the extension theorem 1. The extension theorem suggests something like this, that if from a comma infinity to r, so this will be same if I take minus infinity to b. Okay, so it's things like that. So a comma infinity to r is uniformly continuous if sorry, so closed interval a comma b is uniform. Okay, so let me rephrase it. So if closed interval a comma infinity to r, a continuous function is uniformly continuous if limit x tends to infinity, f of x is exists and is finite. Okay, so this is one of the this is the second extension criterion, which suggests that if I have a semi-closed, semi-open interval like closed a to infinity or minus infinity comma closed b, so that continuous function turns out to be an uniformly continuous function. Whenever limit x tends to infinity, the functional limit exists. So this is precisely the way we will solve our problem by the extension theorem 2. So in this extension theorem, so look at this function very carefully now. So what I will do is I will define gx to be this sine x cubed by x when x not equals to 0, and of course I mean 0 comma infinity. So let's just say x belongs to open 0 comma infinity, and 0 when x is 0. So what does this tells us? That means that so from here, if we just combine the extension theorem, what it tells us is that this thing is that if from a comma infinity to r is uniformly continuous, if and only if there exists an f tilde from closed interval a comma infinity to r that is continuous and limit x tends to infinity, f tilde of x is equal to some c less than infinity, and f tilde restricted to a comma infinity is f. So if I just combine these two extension theorem, if I just take these two extension theorem, this is precisely what we will have for an uniform continuous criterion for functions going from open intervals and closed intervals. Okay, so this is the thing that we are actually using. So that is the reason I have actually. So let me stick with f tilde since I'm writing in bigger f tilde. So if I just take this as f tilde of x. So as you can see now, f tilde of x. So this f tilde of x restricted to the interval 0 comma infinity, restricted to the interval 0 comma infinity is nothing but f of x. If you look at it, then f tilde restricted to 0 comma infinity is nothing but f, right? and f tilde is also continuous at closed interval 0 comma infinity. This is pretty clear, right? Just computed limit x tends to 0, what is f tilde of x? Okay, so just if you just compute it, so now what I have, so I have something like this, that f tilde of x is sine x cube by x when x belongs to 0 comma infinity, and 0 when x is equals to 0. So is f, so now the question is, so f tilde restricted to 0 comma infinity, this is f. So this is the first part, so this is this part. Also what I need to show, I need to show that it is continuous in this. So now of course it is continuous here, there's no problem in continuity here. So now the only problem point is x equals to 0. So if I take limit x tends to 0, f tilde of x, this is also 0. Okay, that is equals to f of 0. Hence, it is continuous. You can actually use this same old computation that we did here. Okay, so from here, so now what do I have? I have two things, that f tilde restricted to 0 comma infinity is f tilde is continuous at 0 comma infinity. So the only thing that I am missing now to put everything together is this: what happens whenever I take x tends to infinity, f tilde of x. So this is 0. Okay, because by the same sandwich theorem, you can say that f tilde of x becomes 0. So what happens is, now by the extension theorem, f is uniformly continuous. So first we proved that it is bounded, and then we proved that it was uniformly continuous. Hence, the solution to this question is it is bounded and uniformly continuous. So please do give a read to these extension theorems if you are interested. It is available in Bartley-Shepard or any standard analysis book. Thank you for joining. We will meet again next time with another problem from TIFR.